Okay, let's get going. Did everybody get the email where I told you where you can go, the link to get PT data and download the student version? Has anybody downloaded that yet? Okay, that's fine. This year I've decided not to make it mandatory that you use the program, though I'm going to highly recommend it. I ran into a little trouble last year with a group of people I really liked, but they didn't tell me that they had a problem with the program, and one of them had the program and 2 or 3 didn't, and the one person who was using the program didn't use it correctly, so gave some values that were incorrect to the other 2 or 3, and they all came up with exactly the same wrong things on the project. And it's very clear when that happens that people are doing what I've asked you not to do and working together and just doing the same exact thing. I really want you to work on this project independently. Checking answers with someone else I think is fine. I think it's a good idea. You know, checking in, seeing if you're having a problem, work with your friends, find the problem. That is all fine, but every single pencil mark that you do needs to be your own. I need to see your own thought process. You're probably going to generate about 35 pages of calculations. They should not look like anybody else's 35 pages. Even 2 of them shouldn't look the same. There's numerous ways to approach every part of this design, and you really have the freedom to do it on your own. Some people want to calculate the FPS values at all the supports and all the spans first and get that out of the way and concentrate on that. Other people want to look at the left support first, and they do everything about the moment capacity to the left support. Then they move over maybe to the right, the center support, the left side and the right side of it. Other people will go to the mid-span at the next point. I expect to see everybody approach it a little bit differently. That's how I know you're working by yourself. When I start seeing people doing exactly the same things with exactly the same numbers, and then one of the numbers is wrong and that number shows up on 4 different projects, that's an issue. That's what last year this happened. It was like pulling teeth to get out of these people who I really liked what was going on. And it turned out it was really not anything I would ever consider cheating. It was fine. One person had the program, the other 2 didn't. And I said, if you didn't, get some help, get somebody who does, come to me. But they relied on somebody giving them a bad answer. That's all it was. No harm, no foul. Nobody got penalized. Everything was fine. But I've learned something from that too, so I'm not going to make using the program mandatory. I already have print and scan every output page. It's about 19 pages out of PT data. That's going to give you everything you need, and I will just post that on the class website. You can download that, you can print that, and you can use that to turn in as you're checking your answers. But I would encourage you to try to use the program if you can. If you have a Windows-based computer, I think it'll be good for you on resumes to go to a job interview and state that not only did you take this class, but you used the program that we sell and you're proficient in it. You can add it to your resume of programs that you're proficient in, and I promise you very few people are going to have that on their resume. And then if you go to a firm that uses it, you'll have a little bit of a leg up. Part of what I'm doing out here, other than just brainwashing you into thinking of the way I think things, that's a joke, but it's kind of true, is to try to give you a leg up. It gets very competitive out there. You can be one of 4, 5, 8 young people in a firm, and that firm may only see a post-tension structure once every 6 months or once a year. If you're in a general design firm, you'd be working on malls for a while, and then 4-story wood-framed residential structure, and then maybe a hotel, and then maybe a post-tension structure comes through, a hotel or a parking structure, and they will team up. Most firms will team up an experienced engineer with an inexperienced engineer, an experienced draftsman with an inexperienced draftsman, and almost every building I ever worked on, except for the really big ones like Getty and things like that, 4 people worked on those projects. That was it. In my office, 2 of us work on those projects. So what I'm trying to get you to do is be that one when they look at 5 or 6 people and they say, well, we've got this post-tension structure that's come in, or a pre-stressed structure that's come in. who would it make sense to team up with our seasoned engineer? And you want that to be you, I promise you. You want a breadth of knowledge, first of all, for passing your structural exam. Secondly, for just making yourself more valuable within a company. You want to be able to do all kinds of things. So when the economy turns down, you know, you've got this vast ability to do a lot of different things, and you're valuable. They don't want to get rid of you. And that's my point here, is to try to get you to be tapped on the shoulder when it comes time in your office to do a post-tension structure, and they're going to put a young person on it. So I want that to be you. So if you can, download PT data, install it on your laptop or your home computer or your friend's computer or something, and try to use it. It's very easy to use. You're going to see it today. I think you'll enjoy it. You'll get a real feel for how easy it actually is for people who don't know anything about what they're doing to design pre-stressed concrete. And that's the truth. Okay, we're beginning of the 7th week. I think I told you on day 1 that the class will start becoming very serious, moving very quickly. So are your other classes. I know about that. But this is the pressure time. You are finishing homework number 5. I've already given you homework number 6. That's the sheer homework. I've given you a lot of time to do it, but it's going to take a lot of time to do it too. So you know yourself, work in bits and pieces on each one if you want, attack all of one at one time if you want, but be doing something, because if you're not doing something in this class in week 7, 8, and 9, something's gone very wrong and probably won't turn out well. And you've got midterm number 2 coming Thursday of next week. So I know you've got a lot. I've given you a lot. And we're about to start the project. Project is really no big deal if you move along with me. It becomes a very big deal if you put it off till after the second midterm and then decide in the last week you're going to come and attack the whole project. I am very open to helping, sitting down, answering emails 24/7 in the beginning. Few days before the project's due, when I'm answering beginning questions, I'll be honest with you, I'm very frustrated, and I'm not as, I'll probably answer your question, but I really don't want questions on the very beginning of the project 4 days before the project's due. It's not good for you to approach it that way. So time management becomes critical, and I do this for a lot of reasons. You need to be good at shear. Even though I can't stand the way shear is done, I still want my UCLA and Cal Poly students graduating to be the best at it anyway. And you will be after you do this homework assignment, I promise you. You will know more about shear design than just about anybody you'll run into. So at least you'll have that until they change it. But I'm also preparing you for your first job. In your very first job, you'll probably get put on one project under one person, and you'll come in each day and work on that project. But as you get better and more reliable and more projects come through the door, they're going to start putting you on 2 projects at one time, then maybe 3 projects at one time. And time management and budgeting and figuring out what to do when becomes an extremely important part of your progress as a young engineer. And you want them to trust you. You want them to want to give you more work. But a big step in a young engineer's life is having 2 projects instead of 1 project. You've got a design development set coming on a certain date on one project, and you've got a 75% construction document submittal coming on another date, and it's up to you to prepare enough calculations for the design development set, get enough information to the draftsman, at the same time getting enough information for either the building department submittal or the 95% submittal. And that becomes up to you. There are very few people who are going to, believe it or not, come by and make sure every day that you're right on track for where you need to be. It's just like school. It's up to you to do it. They'll know when you don't do it because the submittal time will come and you're not ready, and that doesn't look good. And one thing you'll learn as a young engineer, one of the most valuable things you'll learn as a young engineer is you will get yelled at like you've never been yelled at if you get on the phone with one client and tell that client that you can't work on their project full steam because you're working on somebody else's project. That is the last thing that a client ever wants to hear, and that is the last thing your boss will ever want to hear you say on the phone to anybody. Every client comes first. Every client's treated like they're the only client. Those clients know they're not the only client, but the last thing I want to do is hear that you can't work on their project because you're working on somebody else's. So just like that, I know you've got other stuff. Let's practice. Treat me as a client. I don't want to hear that you've got 2 other midterms and you've got another project and you're really getting beaten up. You want to treat this like it's your only class. That's how I want to see it. It's not true. I know it's not true. But start practicing now because that's how clients need to be treated. Okay. From very sharp people who've done very well on tests, I'm getting a number of questions about homework number 5. And they're theoretical questions. And I want to make sure as we go into the project is going to baffle you if these things are not clear right now. I've reviewed homework. I've talked to people, and this is more than just a few, who want to know why they cannot use the concrete-only equivalent loads to come up with the moment diagram on this system. So I will kind of go through it one more time. When we came up with equivalent loads, we put the loads up from the tendons onto the concrete. We acknowledged that these tendons were out here with the same equal and opposite load being put on them. So when this is superimposed, these don't exist. Go back to homework number 2, the last part of homework number 2. I said, draw me reactions, shear, and a moment diagram as if this was a statics class. And you all drew a reactions, shear, and moment diagram just with the applied loads. And I said, statics still applies. That's the whole system. What we did to come up with stresses in homework number 2 is I gave you 2 ways. One way was what we called the free body diagram method, where you actually calculated the real reaction. Go back to your homework. You had to calculate the real reaction. We cut a section. This was a statically determinate beam. But that wasn't a concrete-only reaction. That was a reaction due to the applied loads. Then you figured out what the moment was here, and we had an FE going this way. We had a total load moment, and we had an FE. And you set up equations, and you used a little bit of calculus and found a maxima and calculated what the stresses were. That was the whole system. That was doing the problem with the whole system with the real reactions. And we all decided that was a lot of work, and that was kind of miserable. And then we looked at the other way of doing it, the way that T.Y. Lin came up with. He said you can separate what the tendons are doing to the concrete and what the concrete is doing to the tendons. If you separate these out and you take this part of the load and you toss it off to the side, and you leave yourself with a fictitious loading condition that doesn't really exist, but it's extremely valuable for calculating stresses, you can calculate stresses. So your homework number 2, you did both, and you should have proven to yourself that you can take the equivalent loads from the tendons, put them on the concrete, get a concrete-only shear and moment diagram that's not real. It's just what the concrete thinks is happening. And if you use those moments, you end up getting the same exact stresses that you got using the much more complicated method that had everything in there and the real reactions. Just look at your homework number 2. If you know, it was simple, and the problem is I think I give some simple homework and it doesn't look like it's that theoretically complicated, but they really are. That was only useful for stresses. It was useful for deflections too, but we didn't calculate those. But that's it. When I said we went to strength, we're back to static correctness. This all goes back in. We can't take a whole bunch of forces and throw them off to the side and toss them and act like we're satisfying statics. We're not. We're not satisfying the full system. Now in homework number 5 and number 4, we're back to putting on the applied loads. The applied loads are the only real loads in homework number 4. In homework number 5, the applied loads plus one other thing created real shears and moments. What was that one other thing? It wasn't just the applied loads that you used to come up with the demand moment. What else did you have to account for? The secondary effects. The secondary effects created real reactions, not fake concrete-only reactions. They created real reactions because when the beam was stressed, it tried to lift up, and it couldn't. It was held down by the middle support. So it generated real reactions. So those created moments that needed to be accounted for along with the applied load moments. So the equivalent load moments, concrete only, useful only for stresses. Then we came back and we did use those again. Those were very useful in finding the secondary effects. So yeah, they were useful for one other thing other than calculating stresses, for actually determining what the secondary moments and reactions were. But we're back to the full system, the full statically correct system, not a concrete only type of system. I mean, if you're a little fuzzy, before you start the project, just flip through the homework assignments. They actually led you right to this point. I had a method for my madness of going through what homework number 1 was. That was a beam that had no weight. It had no applied loads. We just looked at what the tendons do to a material and what the material does to a tendon. And you guys got that. And then we went to homework number 2 where we put applied loads on, and we did it 2 different ways, a complicated way and a much easier way. And we stuck with that much easier way, and we worked into multi-span systems and showed that you can still calculate stresses in multi-span systems just as easily by using the equivalent load method. Then we went to strength design. So we're in strength design, flexural design, shear design, all based on the real applied loads, not a concrete only or equivalent load only philosophy. Okay. I'm about to start the project. This will take at least 3 lectures to get through. I'm going to get through some of it, and I would expect you to try to get through that same amount in the following few days. My example is somewhat like yours, but not the same, and I will point out what's different and flag you to what you're going to have to do differently. But both of us are going to have a 2-span beam. This is a plan view. So I'm looking down at a plan. These beams just keep repeating. I've drawn a section of the floor system, and these will keep repeating until the geometry of the building changes. Maybe it will grow out here later towards the north or the south, and you frame it differently. But this is a section of it. Each beam is spaced at 18 feet on center. So we'll design this beam. This beam has a tributary area of 18 feet. 9 feet on this side that load is going to be assumed to come here. 9 feet on this side is going to be assumed to be supported on that beam. Tributary area. This is the elevation. So if I cut a section through here and I'm looking at the beam that I'm designing, this is what it looks like. 11-foot floor heights, 11-foot floor heights. That's very typical for long span parking structures with handicap parking. That gets you the beam, the 36-inch beam depth, plus a little construction tolerance, plus the required height for a disabled van to get in and open. So I didn't just pull this out of nowhere. That number will probably show up on most of the long span parking structures that you ever work on. These are the columns supporting the beams. A section through that column looks like this. It's 24 by 24. Yours is 24 by 24. That's a nice easy number for calculations, and I decided to give both of us that number. These are the only things you're going to be given when it comes time to design at an actual design job. You're going to know these things. You're going to know what this beam section looks like. But remember, this slab just keeps running on and running on. You're going to have to create a T-beam out of that floor system. You're going to have to do this on the project. Your flange should be BW, which is the width of the web, plus 2 times 8 times the slab thickness. So you're allowed to go, this is allowed to be 8T and this is allowed to be 8T. So you have 16T plus the width of the web for an interior beam. In my case, this is 95 inches. At that point, you are going to have to calculate the area of that beam, the moment of inertia, the distance from the centroid to the top, the distance from the centroid to the bottom, and the section modulus top and bottom. So homework number 1, right there. The material properties, we both have 5 KSI this time, concrete beams and columns. The tendons are 270 KSI, and both the longitudinal steel and the stirrups are 60 KSI. So we are both being asked to determine the pre-stressing force and drape in both spans. Now, I'm not going to have 58 people come up with their own independent design. So we are all going to do the same one. I am going to come up with that. If I get to that today, I will. But I am asking you to estimate it yourself and do estimation calcs based on some criteria that I give you so that you can show me that you could have come up with something very close on your own. You know, this is real design, and the difference between real design and analysis is taking a really good guess in design. If you can take a really good guess on your first pass, and then that turns out to work well, then you did a nice design. Design is not taking wild guesses, taking crazy guesses, having no idea where to start. Your boss in every material will get you going in the right direction. You know, steel is typically designed in floors controlled by deflection. So your boss will say limit the deflection, the dead load deflection to, you know, I don't know, L over 180, the total deflection, L over 360, something like that. And you'll estimate and come up with beam sizes. And then you'll do all the checks and the checks for strength and all other things. And you'll find that, well, that works. In wood, it's the same way. Oftentimes, shear governs in wood. So you'll make sure you find a size to where the shear is going to work, and then you'll see that everything else works. But no matter what you do, there's usually good criteria to start. And our criteria, at least I've given this to you in your project. Mine on this, you know, your boss may change it, she or he may decide how to give you a way to go. Your office may have certain standards that you follow. These things are usually never code. They're just an office standard. Our office balances at least 65% of concrete load. That is my office's minimum. That's many offices' minimum. I've actually chosen 70% for this design problem. So I'm going to attempt to balance approximately 70% of just the weight of the concrete. I haven't talked about what the live load is yet on this, but I want to balance about 70%. I've asked you to balance, I don't know what I said, 65 to 70%, 65 to 67%. I'm helping you get right in the range. And our office provides in beams a minimum P over A compression of 250 PSI. So over this beam section that we will determine, you're working in my office, we're going to provide a minimum of 250 PSI. So those are your 2 criteria for coming up with a force and a profile. Balance 70% of the dead load, of the concrete load, and put in at least 250 PSI into the beam section. If you've got questions, now would be a good time to ask, because this is, you know, this is design. And these are the things. You'll know the column size, you'll know the beam section. Someone will give you the material properties. You or the program will calculate section properties, but this is about all you know. The first thing in anything that you're going to design, steel, wood, concrete, pre-stressed concrete, you'll need a loading criteria sheet. If you guys saw Brian's calculation books, The first thing was the load criteria sheet in everything we ever do. This is the way most practicing structural engineers will do the load criteria. Regardless of what it is, the slab, the beam, the column, the walls, you break that into a pound per square foot on the building. I'll discuss why that is in a minute. Because you have to design the slabs, and then you have to design the beams, and then you'll have to design the girders, and then you'll have to design the columns, then you'll have to design the foundations. Here?
Yes.
At.
Okay, is that
18 feet on center. Sorry. That stands for this. This is the beam spacing at 18 feet on center. The O/C is just something you have to get used to. It doesn't matter what material you're talking about. That's a standard engineering thing to describe spacing. Okay, so all I'm doing here, this confuses everybody every year, but the line load on this beam is going to be the weight of 18 feet, a section right here, 18 feet of width. So the way I've done it, as I said, the 5-inch slab part weighs 62.5 pounds a square foot. The rest of this, I calculated the weight of this at 150 pounds per cubic foot, and I divided it by 18 feet to convert this chunk of concrete into pounds per square foot. If I did that correctly, that should be 15 inches times 31 inches times 150 pounds per cubic foot divided by 18 feet. So the beams are equivalent to 26.9 pounds a square foot. If you will do it this way, you don't have to do it this way for the project. I need you to get to the next step where you get a line load of dead load. But this is how I do it. This is how design offices do it. Everything typically gets converted to pounds per square foot. Then when you go to design this column, you know what the beams weigh in pounds per square foot. You know what the girders weigh in pounds per square foot. You know what the column itself weighs in pounds per square foot. To get the dead load on it, you just multiply the tributary area by the pounds per square foot of everything framing to it, and you will get that number. That becomes it's a very easy way to keep track and keep bookwork and keep things flowing in your design calculations. So the concrete only part of this, just the concrete weight itself, is 89.4 pounds per square foot. We always throw in something for a little extra, little conduit, little plumbing, little something that's, we can't anticipate. I've put in 2 pounds a square foot. I've told you whatever it is I want you to put in on yours, 2 or 3. So the total dead load is 91.4 pounds per square foot. You know, that comes from the system itself. Dead loads, you have to calculate whatever it is you actually have. Live load comes out of the code itself. Live load, the code will just tell you what the design live load is. Depends on the occupancy. If it's in a hotel or an apartment, it's going to be 40 pounds a square foot. Parking is also 40 pounds a square foot. Retail stores are 100 pounds a square foot. Balconies are 60. You'll end up memorizing these. There's not that many. Storage, light storage is 125. Heavy storage, 250. But there's a live load table, and whatever the occupancy is that you're designing, you look that up, and it comes out of the code. So we're doing a parking structure. The code tells us that's 40 pounds a square foot, and that's unreducible. So. Okay, service loading, unfactored. What do you think we're going to use the service loading for? Stresses. That's right. The concrete only, and I want you to calculate this because we're going to estimate the pre-stressing based on just concrete weight. It's the only thing in most of the buildings that you're going to design that will always be there guaranteed. We only pre-stress and balance loads that are always there 100% of the time. That's our philosophy. 1.609 kips per foot. The dead load in the system is 1.645 kips per foot. All I've done is calculated the line load on this beam. The live load is 0.72 kips per foot. Okay, factored line loads. 1.2 times the dead load. I don't really care at this point about the concrete only. The concrete weight only is what I'm going to use to figure out how many tendons, just balancing percent of the dead load. Factored loading, 1.2 times the dead load, 1.6 times the live load. Add those up for a total. What am I going to use those for? Strength design. What kind of strength? Just flexural strength and shear strength. That's right. Okay, I want you, just as we've gone along, to use a 4-inch maximum CGS maximum. It can be less. At the top, it's not going to be less. Pretty much just what we've done all along. I've told you about 4 inches is a very reasonable and comfortable CGS to the face of concrete. So we're going to assume that. Okay, I need to figure out how much pre-stressing steel I need. Which span should I start with? Which span do you think I should look at? The long one's going to control this, right? You guys did homework number 3. It was genius. You had a long span. It controlled. It's where the stresses were actually not working, and we played with the shorter span to make the longer span work, okay? Homework number 3 right now. Okay, I'm in the long span at 62 feet. What am I going to put for the distance to the bottom here? 4 inches. This is the controlling span, so I want to go as high as I can. I want to be at the center of gravity of the concrete at the end. We don't want to have any applied moments. I'm going to fully drape this span because it will be the controlling long span. Tends as high as it can get over the support, 4 inches from the top. I'll put this back down a second. Okay, I want you to write this down, and then I want to make sure everybody's clear. Everybody has this part. Can I get rid of this? Okay, remember, this is what makes design different than analysis. I could just give you this, but I'm not going to. I want you to prove that you could get close, that you could get to a good starting point. And all I'm telling you is balance 70% of the concrete weight and provide 250 psi over the section. Okay, I already know what a full drape looks like. I don't need to know what the force is to know that the most A I can get is 24.3 inches in this span. I've asked you, or I've asked me, to balance about 70% of that concrete weight. That concrete weight was 1.609 kips per foot. Just the weight of this beam and that 5-inch slab is 1.609 kips per foot. So I'm going to try to offset that by 70%. So 0.7 of that, 0.7 times that is 1.126 kips per foot. That's what I want to shoot for a balance load. So we know that the equivalent load is 8 Fa over L squared. I rewrite this for a force. The force is equal to W equivalent L squared over 8A. I'm estimating that I'm going to have an equivalent load of about 1.126. That's 70% of the concrete load. I know what A is. The only thing left is it would take me about 267 kips to balance about 70% of the concrete weight. This is an estimate, and this theory, this approach seems to, there are just some people that have so much trouble with this. And I'm trying to tell you that design is taking a good guess. And what I'm asking you to do on the project is show me that you could take a good guess. I'm going to determine the number of tendons that you're going to use. I am going to determine the drape. I will show that to you, and we will all, 58 of you, will use that same thing. But that's not design. That's me doing it for you. What I want you to do to make this a design problem is to show me that you could have gotten to very close to the answer that I'm giving you to do. So we haven't gotten to what I'm telling you to do yet, but this is how I want you to just show me. And I will get lines of people who come in and say, I'm only balancing 69.3% of the dead load in your example. You said 70, or whatever I've asked you to do. The theory is this is an approximation. You're just trying to come up with the nice round number of tendons that you need. There's going to be 9, or 10, or 11, or 12. This is the estimate to get close to that number. Okay, this wasn't the only thing that I stated that I wanted done. I also want 250 psi. Most offices require a minimum of 250 psi on the cross-section. The cross-sectional area is 940 square inches in this section. Another thing that people get confused every year, this is the beam section for section properties. This is the full tributary area for the weight that beam has to support. Every year, I get a number of people who are confused between this distance, which is what the code limits you to in section properties. Moment of inertia, section modulus to the top, section modulus to the bottom, A. Code gives us direction, says use 8T on each side for these properties. So that section generated these properties. The full 18 feet is what has to be held up by this beam. That is the tributary area to the beam. That's what generated all of these weights. Now I will get people confused, and they're only going to calculate the dead load over 95 inches. And I will ask them, well, what is going to support all the rest of the distance to the halfway point? So difference between section property width and full tributary width of load that you have to support. Okay, back to it. So Also said that the minimum force is going to be based on 250 psi on the cross section, which is 940 square inches. That would require 235 kips. For my estimate of the number of tendons that I'm going to use, what number should I use? 267. It's the bigger one. 267 will obviously give me more than the 250 psi. If I only use this force, I'm balancing much less than the 70% of the concrete weight. So okay, I'm going to start with a good guess of 10 tendons. I already know the drape in the first bay, right? It's maximized. It's 4 inches from the bottom here. It starts at the CGC. 4 inches from the bottom here, 4 inches from the top there. So I've got a full drape in the long controlling span. That's what I want you to do. That's what we will do. And I'm going to start with what's the force? It's not 267. Don't write fails or no good or need 11 tendons. I get this every year, and some people will really struggle with what is just an approximate starting point. We're just getting close. The closest number to giving me 267 was 10 tendons. It gives me 266.2. I'm approximately 70% of the dead load. There's nothing magic about being 70%. If I'm 69.3%, that's just fine. There's no code requirement. Nothing fails. Nothing's wrong. You're doing these things to come up with the closest approximation. Nate?
The numbers worked out nicely in this example, but if you're kind
Of course they do. I've made it much more complicated for you. What kind of teacher you think I am? I make things easy for myself. I make it harder for you.
we could just, if it's in between, we could just like add a strand and then change the drape.
You'd never want to change the drape. The drape comes for free. So you take the whole drape in the controlling span. And remember, tendons cost money. So you'll start with which one? The lower or the higher? The lower. Then you add, if you've got to add money, you add money when it doesn't work. When will we know if this worked? I'm guessing right now. I've come up with an approximate method for guessing. When will I actually know if my guesses work? When I check stresses. That's right. That's when I will know if my guessing works. Up until then, I'm just taking good, educated guesses. I've been doing this for 25 years. I know this guess will get me very close. It may not be perfect. It may not work. But it will get me close. It's better than starting at 2 randomly, not having any idea what I'm doing, and then working up to 3, and then skipping and maybe going to 6. This will get me within a tendon or 2 every time. Unless I have a very unusual building, these general rules will get you right in the ballpark. Okay. Another thing that people do is then they'll tell me that this is the force. This was an estimated force. This was an estimated equivalent load. This was an estimated amount of concrete balance. None of these matter. Okay, none of these are numbers you're going to use in your calculations. These were numbers we were coming up to go from a wild guess to a pretty darn good guess. And all we got out of that right now was 10 tendons. 10 tendons has a force of 266.2 kips, not 267. But I've had people who will now take 267 because they calculated it, needing it here, and they will run with that in their calculations. That won't happen to you because I'm giving you the number of tendons. But I want you to, these were estimates. We're now going to start with 10 tendons. This is the only real number we've come up with. And that real number results in a real actual force. So now, for now, that's set. Okay, that span is set now. At least our good guess is set. We'll go to this span. What number is here? Well, we got the force from the other span, right? And this is what I want you to do. We could be dropping off tendons and doing other things. We're not doing that. You're not doing that in your project. I'm not doing that in my example. So we calculate 10 tendons. They're going through one end to the other of the two-span system. So this is now set. This is what's not known. Now, you've never taken this class. You've never had prestressed concrete in your life. You've never done homework number 3. You're out at a job, and someone says, I want you to design this beam. What do you put this at without ever taking this class or knowing what you're doing? 4 inches. You fully drape, because more is better, right? Always. More cowbell. That's not what we're going to do. You did homework number 3. You actually showed that when this shorter bay was fully draped, it actually hurt the other bay. So we're going to take advantage of that knowledge. We're going to come up with a number that also approximately balances about 70% of the dead load. So I already calculated this number. The dead load in both spans was 1.609 kips per foot. If I want to balance 70% of that, that was 1.126. That calculation is right here. Okay, to Nate's point, my calculations turned out to be exactly 16 when I calculated this. If I would have calculated 15.5, what number should I use from the bottom? If you had to round, which direction do you want to round? Make that number a bigger number or make that number a smaller number? Go back to homework number 3. What's that? Make it a bigger number. Balance a little bit less load. It's the non-controlling span. So if you're shooting for balancing 70% of the concrete weight and you're balancing about 70 in the controlling span, you might want to balance a little bit less in the other span. Remember, that had a big effect on the stresses in the controlling span. So you don't want to overbalance. You want to slightly underbalance the non-controlling spans and balance as much as you can in the controlling span. So okay, I can't stress this enough, and I keep stressing it because people will make these mistakes. This was an estimate of the equivalent load. Then I came up with a number. You may round this number. You may decide to jockey this number. So when you do that, unless this, like mine, turned out to be exactly a round number, this is no longer your equivalent load. So don't use your estimated approximate equivalent loads for your calculations. You're going to have to, once you get it all dialed in, calculate the exact equivalent loads that you have based upon exactly the drape and the force that you have. So we now, we estimated 267 kips. We're going to use, I don't know what we estimated, but we're going to use 266.2. We estimated an A value, but now we're going to round it to a nice even value, and we're going to calculate the actual equivalent loads. Okay, put a box around this and this 69.7. I want to show you something in the program, and I want you to be able to remember this number. 1.122 kips per foot, 69.7% of concrete load. Okay. Basically, because this 12.3 turned out to be exactly what I started with, I get exactly 70% of the concrete load in the second span, 1.128 kips per foot. Anybody have any questions while I'm waiting for the projector to warm up? David.
When should we want to add a moment and to, well, not to have the tangent at the center of the section?
For all practical purposes, never. Yeah, I mean, once you get really good at this and you decide there's circumstances in which you will take that applied crank, the reason to stay away from that is that it actually starts twisting the slab edge. And the biggest trouble that people have, I think I told you before, are slabs on ground, where the tendons actually do get anchored much higher than the centroid of the concrete, and they tend to twist. I will, this has been the cause of lawsuits, that a slab on ground, you know, in plan has some deep ribs in it. Because they can only anchor the tendons up at the top, they put the tendons just in the slab. But what happens is, in a section, with the section properties, you know, center of gravity being down here and the force being up here, this tends to rotate. And that actually causes problems in houses and apartments and things like that. It's so slabs on ground are a whole different world. They follow all kinds of different rules and don't do any calculations that resemble anything that I've taught you whatsoever. But and they anchor the tendons just up in the slab. So the bottom line is, you don't want, and we put a lot more force in our elevated structures than go in slabs on grade, so you can literally start rotating the edges, and you don't want that to happen. So the way to avoid that is anchor the post-tensioning at the center of gravity of the section, and you'll at least keep that from doing any twisting. Numerically, sometimes, I won't lie to you, I've raised tendons before to get more balance load and drape, but like I said, once you get good at this and you understand the consequences of it, then you can go through, and numerically you might see a little bit of a benefit sometimes, but like I said, there'll be real life consequences of things twisting and possibly cracking and some torsion too. So best answer is no. Don't just don't do it. Okay, this is PT data. If you download it, you've got the student version. It's free. You can have it forever. It does everything the regular program does, except it's limited to 2 spans, but that works out well for us. You will be prompted for this. The first screen that you get will be a screen that looks like this. It'll default to almost everything you need. You will put in 2 spans. You're limited to 2 spans, so that makes it easy. You have no cantilevers, but if you did, you'd click one of these boxes. Your program should default, being the student program, to a uniform live load. Technically, we're supposed to skip the live load, which means put some on one bay, analyze that, put some on the other bay, analyze that, put it on both bays, analyze that. It's a lot more work, and I don't think you're learning anything really about pre-stressed concrete. You're just learning about live load distribution and skipping. So I don't do that in your design project or in my example, but you should be aware of that it's there. The one thing to check is make sure that you've got the top and bottom set at number 8. So I don't think that's a default. It's going to possibly default. It's not a big deal. It really doesn't change the calculations. Change the cover a little bit, or the distance to the CGS a little bit. All this other stuff should default. I've already input all this stuff, but you would be prompted screen after screen for it. But go ahead and take pictures of the screen if you want. I'm actually going to do yours. I don't know if I'm going to get to it today, but I will show you, and you'll see exactly what it's supposed to look like. But this is the book example. Bottom column, floor heights 11'4" for all columns. Top column also 11'4". Yeah.
Minimum, the report value is showing 125 psi.
Yeah, people get that wrong. The only minimum PSI in the code ever is for two-way slabs. That's misread and misinterpreted all the time. There is no code minimum for one-way slabs or for beams. A lot of people read that 125 and think it applies to that. The truth of the matter is it only applies to two-way post-tension slabs. But most firms, our firm, will in one-way slabs and in beams put in, in one-way slabs we have a minimum of about 150 psi. In beams we have 250. So we're nowhere near that lower limit even if you thought it applied, but technically it actually doesn't apply. So here's the column input. The fixity just means the far end fixed, which, when I drew this is fixing the end of the column. If I wanted the far end pinned, what I'd be doing is doing this, allowing that to rotate freely. The code says for equivalent frame analysis, you shall take the far end as fixed as long as it can be, or you're allowed to take it as fixed. So that's what the F is there for. I've got the 62-foot span in the first span, 44-foot span in the other. I suggest you input this the same way. Just call your beam section name A. It takes one letter. It'll take up to 2 letters, but just A is a nice, easy one. And the geometry that you're defining is beam type 1. You have a lot of different beam types to choose from. For us, we're just using type 1. So when I say to define that, this is put in the 18-foot tributary. This will actually calculate the flange for you if you just hit enter, if you've already put in the other things. 36-inch beam depth, 5-inch slab, 15-inch web. So you're defining the section in here, in this. Well, you can use any of those sections that showed over there. Be careful when you put in the loading. These, first of all, are superimposed loads. The program will calculate the concrete weight. It knows that you've given it all the information it needs. It will calculate anything that it can calculate for you and make your life easy. So it's going to calculate the concrete weight. You are just putting in what's called the superimposed load, what it can't know. That's the 2 pounds per square foot. And it goes in kips per square foot in this program. So be careful. Don't put 2. You're actually putting 2,000 pounds per square foot as opposed to 2 if you put in 2. The live load is 0.04. And all you're going to do is click on that uniform load right there. You will tell the program, for us, we're just using profile type 1. When you get out and start getting fancier, you can put in what you think the real construction is going to look like. And these change depending on whether or not they're beams or two-way slabs or one-way slabs. If you're doing try to balance a point load or a beam framing in and you're designing a girder, you have options for this. You have cantilever options, but we're sticking with 1. So you're just putting 1 in here in both cases. Eight. It's the reverse curvature at the support. 8 Well, 8 would be what we did here. What you've done up till now is 8. It is a pure parabola. So, not really, but neither is 1. But life gets much more complicated if we were going to try to use the reversals. Now you've got equivalent loads going down, you've got equivalent loads going up. It complicates the numerics much more, but the answers don't change a lot. And you can play with the program and prove that to yourself. But you'll see some minor amount of change, but what we're doing is anatomically pretty correct. Close enough for government work, absolutely. Oh, that didn't work. I must have played with this too much. Okay. I guess I was playing with this earlier and should have not saved it. But this is the force and profile screen. The problem with a laptop trying to project it up onto this is it doesn't seem to get just about everything. But these are all the tensile stresses. They've already been calculated. I already know what they are right now, and they all work. The program's finished. The program has basically done and designed the beam already. I basically put in the geometry, put in the loading. It gave me what it thought was the best design. By the way, this is a true design program. It is not an analysis program like 95% of programs you're going to use. It's trying to design it for you. So one thing that students sometimes are frustrated on is if I tell it, calculate the force and profile, it's going to fully drape the system. And it's going to try to drop off tendons, and it's going to fully drape both bays and then give me the least amount of force it can in each bay. It's a design program. It's trying to come up with the most efficient, cost-effective design. So if you leave and you bounce around and you look at different things in the program, and then you come back, it's going to try to redesign you. It's going to think you changed something, and now its job is to come in and give you a really good starting point for design. So if it does that and all of your numbers get screwed up, you don't have to re-input them all again. There's a little button down at the bottom which just says Previous Force and Profile. Click on that, and all your work will come right back. The force and profile that we're using for the project will come right back, and everything will end up being correct again. But every once in a while, if you leave this screen and you go back in and you change the load or you look at anything, it thinks you've made enough of a change that it's going to try to redesign the beam for you. So what I wanted you to see at this point, that concrete load balanced of 69.9, yeah, 69.7, close enough. Actually, you know why that's not right? The other thing it will do, it will round your ends to a 1/4 inch, which is what happens in practice, but now I'm at 69.7. So one thing you'll have to do is the end values, it knows that if you're within a 1/4 inch, it's going to round to a 1/4 inch because that's how you're going to draw it on your drawings. That's how you're going to give it to the draftsman. It knows that, so it's going to round those. There'll be a very slight eccentric moment at the end, but we're talking about a force times less than a 1/4 inch. What I want you to do is override it and put in, just like I just did, put in exactly what y sub t is here. And put in exactly what y sub t is here. Then everything will be exactly per your calculations. There's a whole bunch of stuff in here, and we'll get to almost all of it. But right now, what I wanted you to see is that concrete load that we calculated, the 1.609, the program calculated. It's right here. When you do your numbers, you can check the program, and it should tell you exactly what the concrete line load is. If you've made a mistake, those numbers will be different. Given the tendon loads, it tells you exactly what the equivalent load was. That 1.122 was right there. The 1.609 was right there. So it's calculating the same things you are. In fact, just about every calculation you do, you will find in the program somewhere. So that was span 1. In span 2, I asked you to make sure that you highlighted the 1.128. And it's telling you that that's 70.1% balanced. But, so, when you calculate your balance loads, your equivalent loads in each span, you have a place in the program to go check and make sure you're exactly the same. And I'm going to say this one more time because I had a person last year. I had 54 people last year, 53, 58 this year. One person did their own design. This was really a language barrier problem, I think, and ended up doing all the calcs, 35 pages of them, based upon a different force and profile than I told the entire class they have to use. Does everybody understand? All these calculations that I've asked you to do, they're going to go in the beginning section of your calculations under an estimate a design. You're just estimating. I am going to show you the exact design that I want you to do. You are just trying to show me that you could have gotten close to that on your own. Okay? You're going to get close to it, but you're not going to use any of your numbers. You're just going to show me that it's pretty darn close to the starting point. So that tells me that had you not had me to help you, you could get close after taking this class. You could get close to a starting point and go forward without me or without anybody helping you. That's all that part of the calculations are. Then you draw a line, say this is what we're doing because it was given in class, and you start forward with what was given. But I want this to be a design project, so I want you to demonstrate that you could have come up with the design yourself. Okay, back to this. I know everybody's tired, but you're going to need to wake up for this part. And this is the part that you need to get correct before you do anything else. And I mean that so much that I want all 58 of you to email me your values before you go farther. In some steel programs and virtually all concrete programs, the joint is considered a rigid joint. Okay. Everything we've done up till now has been on prismatic members. That means that the moment of inertia from one end to the other end doesn't change. Homogeneous members, the material doesn't change, nothing about it changes. That's not happening anymore. We now have rigid zones. What that means is that this part of the beam and this part of the beam inside, if I'm drawing this beam center line to center line, that much of it is infinitely rigid in the analysis. So that is that means that the stiffness factor is no longer 4EI over L. When I rotate this 1 radian, if this is infinitely rigid and this is infinitely rigid, it's more difficult to rotate this 1 radian or 1 degree or 1 unit. So in your project, I've given you those factors. You don't have to calculate this, but I've given this to you. I've said the beam in span 1 has a stiffness factor of whatever I gave you, EI over L. The stiffness factor in span 2 was whatever I gave you. That's okay. And that means that the carryover factor is not equal to 0.5. When I put a moment on here, I don't get exactly half that moment over here. So nothing that we've been doing applies anymore. Of course, I didn't bring a copy of your project, but I've given you a table. Your first part of the homework assignment is just to read all that stuff I gave you in that project. That'll help you get the highest grade possible. It's just clearly reading what I'm asking you to do and just following those steps. I've basically given you a cookbook to go by and a checkbook. I've given you the rubric at the end so you know exactly how we're grading this. But so in my example, I did this differently in the book than I did it in your homework. I've given you these stiffness factors in terms of EI over L. What I'm doing here is, by the way, how would I calculate these? If it's not this way anymore, how am I going to come up with what it is? Well, I got tired of doing what I'm going to say to you, and I actually wrote my own program using moment area. But hopefully you've learned moment area before. Just go back to your structural analysis book. It's not a lot of fun, but it's useful. But the easier way to do this is go to Visual Analysis or RISA or SAP. Build the beam. Build a 62-foot long beam. Make 1 foot of it infinitely rigid. Give it some reasonable moment of inertia in between there. Tell the program to rotate it 1 radian at this support. A moment value will come out. The program will tell you it took me 8,396 foot kips to rotate that 1 degree. In fact, that's what these are the columns. I can build the top column if I want. So I could build a SAP model with this being infinitely rigid, and I could rotate that 1 degree. And the moment that SAP told me was required to do that would be the stiffness value. I could look at it that way. If SAP came out and said, well, it took 8,396 foot kips to rotate that 1 degree, that's the stiffness of that column. Now I could convert that, I could take that 8,396 and figure out what factor that is of EI over L, and that's actually what I did for your project. I just took the moment that it's required to rotate that 1 degree or 1 radian and converted that, set that equal to x times EI over L and solved for that x value, and that's how I gave you the problem factor. So you have these. I'm not asking you to calculate any of these. This is presented a little bit differently than I'm having you do it. You're actually going to have to calculate it, but I've given you everything. You need the moment of inertia of the beam, and you need the moment of inertia of the column. And by the way, one mistake that people have made in the past is calculating the moment of inertia of the beam and using that in the column stiffness. That will give you the wrong answer. You have a column moment of inertia you're going to have to calculate, and you have a beam moment of inertia you're going to have to calculate, and use those in the correct equations that I've given you for stiffness. But you will come up with a column stiffness. You'll come up with a beam stiffness for each span and each column. Okay, how would I know what the carryover factor is? Well, from that same SAP analysis, it took some amount of moment to rotate this 1 degree. SAP would tell me what the moment is at the other end, too. I would just divide that moment by the moment that I rotated. That would tell me the carryover factor. That would tell me that for any moment applied here, what happens over here. Same thing we did to come up with 0.5. But now it's not going to be 0.5. Same thing with fixed end moments. I can put a uniform load on this beam, but the fact that the two ends have a 1 foot infinite rigid section will change this. So it's not WL squared over 12 anymore. It's WL squared over something else. Okay, so these are all effectively given, except you got to calculate the moment of inertia. So once you've done that, you'll have those stiffness factors. Okay. Got to be really clear on this. This I'm not going to, I really don't want you going past doing anything until you verified these distribution factors. I had a student, very smart student, I think I told you before, didn't think he needed my help, calculated all the distribution factors incorrectly by just screwing up a moment of inertia, and literally did the entire project wrong. It just crushed me, crushed him too. So since then, I live and learn. I want everybody emailing me the distribution factors you calculate. Now, how did I calculate that? I'm calculating if this is A, notice I'm going to have a distribution factor at A. We're no longer pin supports. We're no longer 0 over here and 0 moment. I've told you that when I showed you moment distribution, I showed you 2 ways. One that was going to get you through almost everything we're going to do with 3 EI over L and some shortcuts. And then I said, I need you to understand this other method because it's going to show up on the project. Well, here we are. Okay, the distribution factor from A to B is defined as what? The stiffness of this beam, which is 3,914 foot kips, span one beam, has a rotational stiffness of 3,914. Divided by what? Just 2 columns and the beam. Divided by the sum of all the stiffnesses going into that joint. So the sum of all of those stiffnesses are the beam itself plus the column above plus the column below. So the beam stiffness divided by the beam stiffness plus 2 times the column stiffness. So when we do the moment distribution and we come up with an unbalanced moment, and we've got to put it in equilibrium, we're going to figure out that moment, but we're only going to multiply the part that goes to this beam by 0.189. It's going to look totally different than you're used to with all the moment distributions you've been doing. But you got to remember that a whole bunch of that is going above and below to those columns too. We're just not keeping track of that. Okay, the distribution factor standing at B towards A. It's the stiffness of this beam, again, which again is the 3,914, divided by the sum of all the stiffnesses at this joint, which include itself, the 3,914, 2 columns at 8,396. By the way, your columns are not the same above and below, I don't think. I think I gave you, so you've got a column stiffness above and a column stiffness below. And divided by the stiffness of this beam. So the distribution factor for any unbalanced moment in the moment distribution, the part that's going to go this way is just 14.8%. Because a lot's going to go up, a lot's going to go down, some's going to go to the beam over here, and 14.8% is going to go to this beam. Okay, this is effectively the stiffness matrix. If this were, you're writing a computer program, this would be the stiffness matrix. For us, we're using moment distribution, but all the same things, expect to get the same answers. Distribution factor 0.189 at the left joint, carryover factor in span 1 of 0.524. Distribution factors. Carryover factor in this span is different than the first one. You're going to have to be careful with your bookwork. When you come up with an unbalanced moment and you multiply by a carryover factor to get over here, make sure you've got the right one. And make sure you don't just use 0.5. And make sure when you come up with the fixed end moments, you don't use WL squared over 12. Okay, I want you to get to here. Some of you will wait till a week before. There's nothing I can do about it. But I would like you, this will not take long. You're going to have to calculate the section properties of the beam and the column. That should go quickly for you. Once you get the moment of inertia of the beam and the column, you can calculate the stiffness factors for the columns and for the beams, and you can quickly calculate what the distribution factors are. I'm going to put this on my phone, so anytime, no matter where I am, in a meeting, hopefully not while driving, if I get to a stop sign, you email me your distribution factors. I will check them against what I've got on my phone, and I will tell you, proceed or you've got a mistake. If you have a mistake, everything from that point forward will be wrong. There will be no point in grading your project because every moment, every shear, every stress calculation, everything you do from this point forward will be wrong. So this is what you need to verify with me that you got correct. Email me anytime, day or night. I will do my best to check my phone as much as I can. I will have those numbers on my phone. I'll let you know if you're good to go or not. Okay? I'll see you on Thursday. Your homework number 4 is up here.